So our third speaker on formal verification is Dr. Surinder Sood, again, someone I've known for a long time, originally from India, now based in Manchester. He's the principal verification engineer at ARM. He's holds a PhD in design verification and validation of hybrid systems from the University of Auckland in New Zealand. He has an overall experience of 20 years. Most of the time he has spent in verification of hardware components to systems on chips. He has worked on different verification techniques while verifying such designs. His research interests include formal verification of digital and hybrid systems. He has also worked in security vulnerability verification of digital hardware and also performance estimation of SoCs while doing SoC verification. He has worked with many prestigious organizations such as Intel, AMD, Samsung Electronics, ST Microelectronics, and SanDisk. Currently, he is working for ARM as a principal engineer and as a senior member of the IEEE Circuit and Systems Society. And the title of his talk is A Semi-Formal Approach to Coverage Analysis and System-on-Chip Debugging.
Hi, thanks for the introduction. So this story starts when I was working for Intel and I was responsible for doing SoC verification. And when we were on the verge of completing project, our management used to ask, hey, can you look whether this scenario has happened? Can you quickly check it? Some test failed. Can you quickly debug it? And when we are doing SoC verification, the problem is if any test fails, to debug the test, we have to open the waves. And when we have to open the waves, the database is too big. Opening the waves in itself takes 10 to 15 minutes. And running one test, if it is fixed, rerunning and running one test on an average used to take on an average 15 to 20 hours. And it was a painful task in answering simple questions. So keeping this problem in perspective, we thought of how we can fix this thing so that we can improve our turnaround time in SoC verification. On top of that, when we are doing functional coverage analysis, we have to merge a lot of UCDBs. And merging of different UCDBs and then checking whether a scenario has been hit or not hit. So it was a nightmare. So this slide speaks about that motivation. So we have a database and we want to debug something. We need to open the waves. We need to do some functional coverage analysis. We need to do a lot of things, and it was, a very time-consuming task. So having understood this problem, so this slide explains all these things we just talked about. Having understood this problem, so we came up with a solution. So in which we thought of doing offline, analysis of regression runs, in which we have lots of waves and, there might be same failures or different category of failures or stuff like that. And then to open those waves and do the debug, it was time consuming. So we thought of this idea in which we used to create a metadata or a report file out of every run. And then we developed a parser. So who was interfaced with that metadata file on one side and to our formal property file onto the other side. And then what we used to do, we used to check whether a given formal property is passing or failing against that metadata file. It appears very simple. Now here comes a top level picture. So what we used to do, the formal property is a system level behavior of the test. So this means, for instance, in a given SoC, if I want to check a boot level flow, so my formal property file will model that system level behavior. The beauty of this is I will be doing everything in natural language. I don't rely on system verilog assertions. I don't rely on standard PSL assertions. Just write in your local language and keep the stuff going. And then the parser, which we developed, so that will parse everything, whatever you write, and then it will tell you whether in a given wave dump, this scenario has happened or not. And it will also help me in quickly pinpointing to the area where the failure has happened. And if there is such failure, it will immediately report out the results into a report file. and then report will be uploaded into the cloud. So that can be accessible by the mentors, by the managers, by the engineers, whosoever is involved in the project. So in this case, the formal property, it is kind of my formal verification system level contract. A contract is nothing but a combination of assumption and a guarantee. So you have an environment and you have a machine running in the environment. Environment defines those set of assumptions, and when those assumptions are met, something has to be guaranteed, so that are checked in that situation. So the parser which you developed, so it models all the LTL semantics. So LTL stands for linear temporal logic, and it is fully coded in the most popular language in the world today, Python. And this Python framework, which interfaces my LTL semantic properties, which are written in the NLP, and it justifies all that NLP property behavior against a given waveform dumps. So we deployed this solution in many avenues while we are doing SOC verification. The most popular, we try to do the entry-exit behavior in a package C state. So any client SOC, any server SOC, so whenever it has to do a state transition from x86 architecture perspective, there are some package C states defined. And to verify those package C states, so we created a system level behavior or a system level contract. And then we broke down that, decomposed that contract into lots of component level contracts, which are realizing the component level behavior. For instance, in this case, we have GPUs, memories, accelerators, and other IPs, which are interfaced by a central resource controller who is actually directing those IPs to whether to enter into the C state, package C state, or to exit from a C state. So this is kind of a request grant kind of handshaking between different IPs interfaced by resource controller in between and fundamentally controlled by a power unit. So what we did is, for instance, in this slide, I'm showing like I have modeled a system level contract which says that on a low power event, a package C entry or entry event should be triggered. So this is at the system level, this is possible when all the corresponding components have done the exit scenario. So this means that we decompose this contract into component level contracts, and we said that for a given IP, whenever it enters into some save state, it should be into the shutdown state within some time. Likewise for IP2, so similar behavior exists. There can be different behavior, but from this example perspective, which is pretty simple, so every IP should be behaving in a similar fashion. And once all my component level properties, if they are checked on my given waveform, then they are composed in a specific manner, which we call as contract composition. There are various compositional techniques which can be used to compose the component level contracts. And fundamentally, that specific composition will refine or satisfy my system level contract. Now, in this example, what I did is all the component level contracts, once they are satisfied, they are proven true against a given waveform, then they are composed as a conjunction. And I say that once all the contracts are conjoined and they are proven, so they automatically satisfy the system level behavior. So here the system level behavior is the package C entry event on every low power event which is injected. So we deployed this in various client and server SOC projects while I was working for Intel. And so this is the outcome which we achieved. So while we were doing the coverage analysis of behavior like this, and we were checking whether a specific functional scenario has happened or doesn't happen, or you want to check a specific behavior, or a test fails, you want to check some specific functionality. So the effort is reduced many folds. And so this approach has given me, not only the coverage closure, first level debug, but it has also enabled me to open new avenues wherein we can have a neural model which can be trained on different types of failures, and it can predict even before running that for so and so configuration, your test is going to fail or your test is going to pass. So this has been successfully deployed in doing performance verification as well. So we are again running one performance test. It takes a lot of hours to run the test and then estimate the performance. So rather than doing that, you just make a neural model out of it, train it, and then ask the model whether this set of configurations will be giving me this latency or this bandwidth over a specific interface. And that too using formal properties, which are respecting the formal semantics. And we are not using any solvers, so scalability is not the issue. So this solution has opened the avenues in multiple dimensions, and all those dimensions has been answered and implemented, and the work is being deployed successfully in the successive projects which are done in Intel. So this solution, so we have also implemented certain SOC security contracts, so which have helps us to detect the vulnerabilities in a given SOC design. And the similar strategy we have deployed in post-silicon. So this means that the penetration of the solution has been seamless while I was working in Intel, and it has a scope for verification of SOC behavior along with the timing guarantees at different levels. So this is what I had for today. Any questions?
Oh,
Yeah.
very dark.
Yeah, sorry.
Any questions from the audience first? We're good. Tobias.
Two questions. First of all, how do you get from natural language to something that you can actually use for verification? So you need to translate the natural language into properties, right?
Yeah. So we know what a test is doing from a test. So as of now, we were manually writing the natural language properties. And then using those natural language properties, the system level property used to decompose it using an automation mechanism. That automation mechanism was using the refinement framework, which is already available in the literature. We inherited those concepts and implemented while doing the refinements. But to create a system level contract, we were doing manually.
Makes sense. Second question. So why would you not check the assertions as part of the simulation run? Why do it afterwards?
Yeah, that's a very good question. And simple answer is we want to shorten the simulation time. One test on an average used to take 12 to 15 hours, and performance test used to take 20 hours to finish. And it was a real problem because run test for 20 hours and then C test failed. What to do? Rerun it again after doing some basic fixes. So to kill that problem, so we turned off all the checks, brought down the simulation time to 10 hours, and then do this.
Thanks.
And no questions, more questions. So there's one from online. How does the approach described is semi-formal in nature?
Yeah, that's a pretty good question. So it's semi-formal because we are writing all the natural language properties using LTL semantics. And LTL has the fundamentals in formal. And we are deploying it on the offline waveform analysis. So that's why it's semi-formal. And we are not using any solvers to prove it.
Okay. And someone's just asked for clarification on LTL.
I'm sorry?
LTL. You just clarify what LTL is.
So that's the linear temporal logic. Yeah.
Yeah. Okay. Okay. Any more questions? Andy, I'll give you.
So it feels like a trade-off is two ways to slow down the simulation. One is to add extra checks, the other one is to add waves. How do these compare against each other?
So there are no extra checks. So we are just decomposing the stimulus behavior as natural language properties, and then testing that stimulus behavior against a given wave. And we are switching off all the scoreboards and checks, meaning at the system level, to cut short the simulation time.
So I was kind of going back to Tobias' question of like, if these properties are in line, but with no waveforms, how would that trade off?
So if properties are inline, you mean to say?
Yeah, so the properties you're running offline
Yeah.
from waveforms, if you didn't have the waveforms in and then ran the tests inline, is there a comparison as to the performance of the simulator there?
You mean to say that so you want to test all the properties which are already written on the existing wave dumps, right? So here the problem is we are inheriting all those assertions from different IP teams. So we are at the SOC, and those IP teams, sometimes the properties are too micro that we don't want them to be enabled. So it was another overhead task, which one to enable, which one not to enable. And we are at the system level, we want to check the system level behavior. So it's better to write our stuff in our own way.
So run once, test many.
Yeah.
Okay. Okay, thank you very much.
Okay.
Thank you.